Hello everyone. In this video I want to show you a full GD&T example. So here we have a bracket, a corner bracket for a table that should reinforce the corner of this table, as you can see, right? And there are some requirements here that are specified for GD&T kind of indirectly, so you have to use them to find all of the tolerance zones and everything. So what are they? This 12 mil radius here, this half circle, it should clear a pin, and the size of that pin is 11.6. Okay, so there will be a pin right here with a diameter of with a radius of 11.6. So let me clarify, this is R of the pin, right? So the radius of that is 11.6 radius pin, or if you want diameter, you have to say basically 23.2 mil diameter pin. And then it's going to clear that. There are four 8 mil holes that you can see on these vertical flanges here and here, and these guys should also they should also clear pins that are rivets, in this case, that are 7.2 mil max size. These three 9 mil holes that are going to sit on the table, we will use M7 screws, and we basically they're gonna be tapped into they are gonna go into the tapped holes inside the table, and these tap holes on the table, they have 1 mil position tolerance. The top flanges should not go above 30.5 mil height on the edge of the table. So if you look here, this top of this flange with respect to this bottom of it should be no more than 30.5, because if it's getting bigger, then this bracket will stick out of the side of the table and will be seen from the side. So we have some limit on the height of that. And using all of this, we want to find, based on how this bracket is sitting on the table, you see the bottom part of it and this face are sitting. We want to select our datum, datum features, qualify them, and then apply any necessary geometric tolerance. Okay. So this is a real life example. Here in SolidWorks, I made the part, okay, with all of the dimensions that are provided here. I made the physical part here, and then I brought it into the drafting environment and added these three views and activated the hidden lines. And now I'm going to put dimensions here as well as geometric tolerance. But what I care about right now are the geometric tolerance ones. So first thing first, where are the datums? Well, as we just talked, the datums are going to be what? Are going to be this bottom of the object right here that it is sitting on the table, and that is the biggest surface, so that's going to be our primary datum. And then we have one here and one here, right? So basically, if you look at them, one of them is this surface and one of them is this surface, basically, or you can refer to it here if you want. Right, so these are our three datums, and we might call them like A, B, and C. And if we go with size, you see A is bigger than B and B is bigger than C. So probably that's the order we want to choose our datums. And there are just three surfaces. So the best selection is going to be flatness for the first one, primary, and then perpendicularities for the two others. Specifically because in this case, these three planes that we chose, these three surfaces, are what are perpendicular to each other, all of them. So here we go, and let's go ahead and apply a flatness to the bottom surface here. So we can apply the bottom surface on this one or on this one. It's up to us. Let's go here and apply it right there. Okay, and gonna bring it out and then say, hey, this guy is gonna be flat. And then we are going to pass to it some flatness here. Now, the amount of this flatness, it depends on really how well polished do you want it to be, okay? So if you go very small, like 0.005, 5,000, that is almost at the limits of a regular CNC machine, and this is quite a bit polished. And a bracket that is sitting on the table at the bottom of the table and cannot be seen, and it's not going to be like something that moves with no friction or something. It does not need that huge tight tolerance. So 0.5, or even you can go as low as 50,000 or 500,000 or anything like that would be fine, because again, it does not need to be really really perfect. So in this case, I go with 100,000 and say, okay, that is my flatness requirement. And then let's go ahead and call this guy A. So here we attach it and we call it A. That's the bottom surface. Then, as I said, this surface is going to be B. Now here you can see that we have to either reduce the scale size of the paper or make the scale of the views smaller, or make the paper bigger so we can have enough of room. And you know what? Let me do that right now. Actually, I guess it's not a bad idea to make the paper bigger. The paper I used was a B, and we might go with a D. Let's see what happens. There we go. Maybe too big, but I would rather have all of this room for now, because my goal is really education here, and I prefer to have enough of room. Okay, and so here we go. So now we go with this surface. As I said, this guy is B. So we are gonna make it perpendicular to A, and again I use the same perpendicularity tolerance that I use for flatness, and this is with respect to A, of course. And as I said, I'm going to call this guy B. Okay, so that is my B, and then finally this surface here is going to be my C, and this guy has to be perpendicular to both A and B. And again, I use the same 100 thou, but this time A and B. Okay. And then again, I add a datum symbol and call this one C. So far, as you can see, I got my datums taken care of and they are qualified. Now we need to go to the other features and try to qualify them as well. And of course, we have to put all the dimensions on, which I'll do next. But right now, I'm focusing on the geometric tolerance, really, because that's the focus of this video. So what else do we need to do? Now, let's look at the features one by one, the ones that are important, the ones that are clearly specified. So these holes, these 4 holes that are 8 mil, as we just saw, they have to clear a rivet that is 7.2 max in diameter. So how much positional tolerance do I have for them? And what diameters can I choose for them, right? What diameters can I choose for them? Well, clearly in this case, it's 7.2. So the minimum diameter of these holes has to clearly be bigger than 7.2, right? And the default for them is 8 mil. Okay, the default for them, the nominal is 8 mil. So I can go 8 mil plus or minus something, or I can even have them 8 plus 0 and then 8 plus something, so I can make both dimensions bigger than 8 if I want to, right? So it depends on what class, what fitting class you have. So we know that the RC class is used for a clearance fit, and as we move from RC1 to RC9, you get bigger and bigger gaps. So we can go to a class like RC8, RC9, or something like that with a lot of gap, and the dimension of 8 mil is between these two numbers in inches. So if we go here and look for class RC9, right, you can see that basically you have this here. Look, so it is point plus 3.5, of course 3.5 thousand, so you have to multiply by 10 to the negative 3 and 0. And if you convert that number into mils, then you get something like 0.09. Now here some numbers are given, and if you want we can go ahead and use those numbers. I can use the limits of 8 and 8.3, but I just wanted to show you if you want to use those tolerance tables, right, then the number you have to provide is like between 8 and 8.09 mils or something like that, and not really something much bigger. So it's up to us here whether to go with here what the problem statement is asking us to do or use a table. So here let's just stick to this. So 4 times phi of 8 to 8.3. So we're going to do that, and then we have to decide to go with how much of positional tolerance for them. So the first thing I want to do is to give them some dimension. So here I click and get it out and say this guy is what? 4 times phi between 8 to 8.3. And then what? And then I will add the geometric tolerance. So let's get it out here and put the dimensions on. Okay, there we go. So I put these dimensions on, and now I want to what? I want to basically add a geometric tolerance for that. And first we have to know how much. If we go back and look at the specs, you see that the dimension of the rivet that they are clearing was 7.2, and the MMC for these holes is 8. So if we calculate the amount of tolerance based on here, it's a floating fastener, right? So if you remember, the formula was T was equal to H minus F, and H here is 8, the minimum dimension, and F here is 7.2. Therefore, I have what? I have a room of 0.8. Okay, here I made the fonts a little bit bigger and I added this break on this leader. So now with that one selected, I should go and create a geometric tolerance. So go here, it is on position. And if you remember, it is how much? It is 0.8, right? And it's a cylindrical region. And of course, we are going to have datums, right? And let's make sure I didn't yet. There we go. And datums are going to be A, B, and C. Okay, and you might say, do I need MMC or something here? Well, since it's a clearance hole, if you add MMC, it will give bonus tolerance for the position if the holes are made bigger. So why not? Actually, it is giving the technician a little bit more room for error in the position if the hole is made bigger. So I recommend to add basically this MMC in this case. That's very appropriate to add that over there. And I assume that now, let me see if I can move this guy. There we go. This is a good positional tolerance for the rivet holes. Then we come back here. Now we go to these holes that are like 9 mil, right? There are 3 of them here. Again, a size tolerance for them is given, so we don't need to go to the tables. And in this case, the minimum size is 9. They are going to be fastened with M7 screws, okay? And so it is going to be 9 minus 7, right? But if you remember here, the table is threaded and these guys have clearance holes. So this is a fixed fastener formula. So we have T1 plus T2 equals the difference between these guys. Okay, so it is a 2 sum of T1 and T2, where T1 is for the bracket, T2 is for the table. And if you can see here, the tapped holes on the table, they already took their 1 mil position tolerance. So one of these guys is a 1, therefore the other one also has to be 1. So you see here, it's not done by split of 25%, 75%. The problem is kind of dictating us to go 50-50. Well, that's not typically common, but if you want to go with what the problem says, then the position tolerance is 1 mil for these guys. So if I go back and now focus on these holes here, so let's go ahead and add dimensions for these guys too. So these guys are between 9 and, as the problem says, 9.5. And there are 3 of them, right? And if you want, you can break that leader by going to leaders and going here to custom text position and clicking on this one. Okay, there we go. Now you select this and go again to geometric tolerance and add that and double click here. And again, it's a position. This time it's 1. It's a cylindrical region. Again, it's a hole, so a clearance hole, so MMC is valid. And again, with respect to A, B, and C. There we go. So these guys are done as well. Now we go to what? We go to the rest of the problem, see what it is asking. Then it says this 12 mil radius in the middle, it has to clear a pin as well. So this guy, where the radius of the pin is 11.6. And this guy is 12, so the gap between them, if I zoom in, right, the gap between these guys is only 0.4 mil in the radial direction. So if I use a circle, let's see if I can use a circle here and draw a circle for you, right? Something like this. Then the gap between this pin and the hole, as I said, is 0.4 mil, right? Because the radius is 11.6, this is 12. So the distance is 0.4 radially, or in diameter, it is going to be what? It is going to be 0.8. So this guy here is 0.4. So diameter wise is 0.8. So I need to, because 0.4 is in this direction, and you might say, first of all, what kind of thing I should use? In this case, it's just a surface like that, and I can apply a profile to it and say, hey, 0.4 on this side and 0.4 on the back side of it. Make sure it is clear. So I have what? I have at least 0.4 on each side of this clearance, and when I have that, then when this pin comes in, it is not going to what? Have any interference. So that's what we're gonna do here, and we are going to add a profile, but do I need to apply it to this entire surface? I mean, to all of this, do I need to apply to all of that? No, only to this portion, this arc here. So I really do not need to apply to entire surface. All I need is really between a point here and a point here, right? That's the area that I care about. The rest of it is not as critical. So here is a good place to do a profile, but using between symbol. So here I go back and I say, well, I add 2 points at the start and end of this 12 mil radius arc, and I'm going to apply a profile over there. So let's go ahead and add those over here. So one of them can go here right at the start of this arc, right? Let's see, there we go. And we are going to call this guy something. I'm not going to call it A because A is already one of my datums. I might call it something else like M or N or something, right? Remember that I can do that. So let's go ahead and add another one on the other side. Okay, that's M and N, and now I'm going to apply my profile here. And this is going to be a profile of a surface, right? And then as we calculated, 0.8 would do the job, and it is with respect to A, B, and C, of course. And we also need to go ahead and add a between symbol. So I need to double click on this guy to get all of those pluses. There we go. And then say between, and say what? Between M and N. And that should do the job for me. Okay, so this is the profile for that. The last requirement we have is this 30.5, that the top of this should not be more than 30.5. And if you look at the size of this flange already is 30. So basically this top of this should not go more than what? Should not go more than 0.5 above the through value that it has. So at most it can go 0.5 above here, and that's it. It cannot be more than 30.5. And how can I control this surface since it's not a feature of size? Well, I have to use a profile again, and this is 0.5 above it. If I also go 0.5 below it, that means a total of 1. So I need a profile for what? For basically 1 mil size on that surface, and that is going to control the height of that as well. Okay, so here we go, and now I'm going to apply a geometric tolerance here and make sure this is also a profile, and this guy is 1 with respect to A, B, and C, and pay attention that it's 2 of that. Okay, because you have it here on this one and you have it on the other flange. So you need to make sure here you say what? 2 times. Okay, it's 2 of that, and you have to pay attention to that part because it's for both of the flanges. Okay, now I got everything covered. I just need to add the basic dimensions, or add the dimensions and then add the general tolerance note and say what? Unless otherwise specified, all dimensions are in mils, all dimensions are basic. And then I need to also add saying, hey, all surfaces are also with some profile and so on, right? So let me go ahead and add those dimensions. There we go. So here I have added all of these dimensions that were in the model. And you might say, why is everything measured from here, specifically in this view? The reason is that is the origin of your datum reference frame. If you look where A, B, and C are hitting each other, right? A is the bottom surface, and then B and C are hitting each other as well as the bottom surface. So that's the origin of your datum reference frame. That's why most of the stuff, as you can see, they're all measured from that point, okay? And so here you see I have added all of those, a typical thickness, the radius for these two corners, 2 times that, this radius here 6 times that, all of those, MN, everything is added. And here I have added this general tolerance node unless otherwise specified, UOS. All dimensions are in mils, all dimensions without tolerance are basic, so I don't need to go and put each and every one of them in a box. And all surfaces that are not as critical should also be following a profile with 1.5 mil, which is 0.75 on each side with respect to ABC. Okay, so you put always this to make sure that the other surfaces that are not directly mentioned here and not as critical also follow some level of accuracy, but of course this is a looser tolerance compared to the other two tolerances. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.